What is resources section? Any question on resources section? You know how, all of you know how to access Hello ITK? Alright. So let's begin transport phenomena officially. Again, before we begin, we have to set it up with an analysis called the dimensional analysis. Now I'm doing that in the first lecture, and usually it's done before we start the formal analysis of transport phenomena. First, one of the first topics that we encounter is dimensional analysis. And by this, what I mean is that it's a very powerful logical tool, but there's no guarantee that it will work, as we'll see with some examples. But there are, if it works, it's very elegant, it's very short, and it has a lot of easy applicability, and it's used by a lot of experimentalists, those who are looking at new phenomena, right? As theoretician or people who work in computational mechanics or computational stuff, you have equations to work with, right? But when you're doing experiments, you're actually in the wild. There may be a theory for it, there may not be a theory for it. So dimensional analysis is a nice tool to see if we can get an answer for that, or to find an explanation for a phenomenon. And when I say it may work or it may not work, it only depends on how expert you are. So as we'll see, if our intuition is wrong, the very first step we'll get it wrong. So the very first step of this analysis is very crucial. So without further ado, let's start the dimensional analysis. But before we start dimensional analysis, let me talk about dimensions.
As we will see in this video, that there are 6 fundamental dimensions that we all have agreed on. There is a scientific consensus on, which is mass, length, time, temperature, ampere, and candela. Candela being the unit for intensity. Sorry, not the unit, the dimension for intensity. And in transport phenomena, we will deal with quantities, and you will see very often velocity, acceleration, force, work, energy, heat, etc. So as you know that velocity is meter per second, or in SI units, or kilometer per hour in your motorbike. You always know that it's length per unit time. So very easily you can decipher that it's LT minus 1. Acceleration, of course, is another time minus 1, so LT minus 2. Force is mass times acceleration, so mass times this is MLT minus 2. Work is mass times acceleration times distance, so the L changes to L square. Work, energy are equivalent, as you know. Work, energy, heat are equivalent, that you know from thermodynamics. So all of these have they can be described in joule, or they could be their dimensions are ml square t minus 2. We will also look at something called as pressure. Again, I will describe in detail what pressure and stress are, but they could be written as force per unit area. That could be normal force, which is the normal stress, or it could be tangential stress. But essentially they are force per unit area. So this is mlt minus 2 divided by L square gives you this. They have a units of pascals, or sometimes it's written as a Newton per meter square. You could also write down the units for mass flux, heat flux, and momentum flux. I'm assuming that from your undergraduate you know Fick's, Fourier's, and Newton's law of viscosity, and you only need to know it on a very on a surface level as a proportionality to get the units of mass flux, heat flux, and momentum flux. I don't expect you to know complete theory and full details with lots of doubts about it. Alright, so if you have that sort of surface level knowledge, it will be helpful, and you can directly find out what is the dimensions of mass flux. But even if you do not know, we will rediscover Fourier's, Fick's, and the momentum flux law, the Newton's law of viscosity, again in this course. Okay, so for example, mass flux is amount of mass transferred per unit area per unit time. So it's m per unit area per unit time. Similarly, you can write down for heat and momentum. You can try it at your home. Once you know this, you can once you know the unit for flux, you can find the unit for diffusion coefficient and something known as thermal conductivity and viscosity. This again I will leave as a homework exercise. because see, you know the dimensions of J. Diffusion dimension is spread per unit time, so it's L square T minus 1. Concentration, it's mole per liter, so it's, or gram per liter, so it's like concentration has the unit of density, X has the unit of length. Okay, with that you can find the unit for the dimension for D, for K and mu using these laws. All right, so back to the lecture.
There is something called as quantities. I'll start with the basic example of sedimentation of a heavy ball into a jar. It's a big jar, and it's dropping steadily, and the medium is static. Okay, this is dropping at a velocity u. So, can you tell me, in this simple, typical fluid mechanics sort of transport phenomena, how many quantities are there that you observe in the system? We'll count them later, but let's list them. So, one, I already told you, velocity. So, u. Force, as it falls down, its face will feel some force because it's displacing liquid. So, let's say Fd, drag force. What else? Density of what? Fluid or particle? Both. Particle and the fluid. Viscosity of the fluid. Anything else? Gravity. Okay. Mass, but density is there, right? But for volume, what do we need? Size of the ball, right? I think that we have enough numbers. Or if you want to also say that L, length of the jar. Now, this is what it seems. And if you talk to an astrologer, he will say Rahu Ketu's location is also relevant here, right? But we are not astrologers. So we work with this physical system at hand, and we say that this is completely unrelated to whatever happens outside. So we stop it. And we say maybe there is some phenomena that are not looking here, but let's go ahead and work with it. Now we have to, these are lots of numbers, by the way. How many? 1, 2, 3, 4, 5, 6, 7, 8. We have to remove some of them, because if you think a bit about it, some of them are redundant. For example, if you already know what is the drag velocity, can you take away the elements that caused it? What caused the drag? What caused the sedimentation velocity? The drag force caused it, but let's say you want to measure the drag force. Velocity can be easily measured by using either a microscope if you are doing a small experiment, or a microscopic experiment. But what caused u? Drag force is the outcome, by the way. The buoyancy caused u, right? And then as soon as it starts dropping, that buoyancy force will be balanced by viscous force. This is the simple fluid mechanics we have done before. So this u, either you take u or you take particle density and gravity. The force that caused u. Right? What is, by the way, just so that you are clear, what is the buoyancy force? So, if this ball is the same density of water, then you have no buoyancy force, right? So it must be dependent on rho p minus rho, yes, into volume, mass. This is mass into acceleration g, right? And then this is balanced by the drag force. So you equate it with something that we don't know yet. But basically, what I'm trying to mean is that this drag force will cause settling velocity. I can either take u or I can take these, and I will, for simplicity, discount particle density and gravity. I'll do one more thing. I'll discount this, because I'll say that I'm only interested in my system where my ball is very smaller than the particle size, the chamber size. So wall effects are not playing a part. So this I am removing under the assumption of L is much greater than A. Okay. So this is the system at hand, and as I describe dimensional analysis, I describe through this problem. Okay. And let's call these number of quantities n. How many n's are there? 1, 2, 3, 4, 5. That there are 6 fundamental dimensions, and any system that you see in this universe, please don't know. Any system that you see in this universe will be made of some combination of these dimensions. Their individual quantities will be made of some combination of these dimensions, and that's what we saw here. So we could write down the dimensions of each of these. Let's write it down. Those who are already aware of this can start writing down the dimensions for all the quantities, all the 5 quantities. Force, mass times acceleration. So you have m. What is acceleration? Meter per second square. Lt minus 2. U is Lt minus 1. A is length. Viscosity is. What is viscosity? Can you open Hello ITK right now? Forgot to tell you this when we started. There is a table I've uploaded. So throughout the examples that we do today, we'll keep looking at this table. Similarly, we can find dimensions of diffusivity, thermal conductivity, viscosity. So why don't you do that as a homework? You can start with basic laws that connect fluxes with their deltas. Meaning, right now we know that stress is equal to some viscosity into some delta strain. Let me call it theta. Theta is for temperature, so let me call it gamma dot. Heat flux is equal to some constant quantity K multiplied by delta T delta X. Similarly, mass flux you can write diffusivity delta C by delta X. Okay. Can you do similarly the same exercise and find the units of K and D at your home? Easy to do, right? Okay. So with that, you can get, I skipped a bit, first part. I had a lecture session to cover all these, derivation of these. But then by the time I finished the lecture preparation, I realized this could be very redundant. So you could rather do it as a homework, as a pretty straightforward homework. Alright, let's return to the fact that let's say we get all these dimensions, and we did this in class 12, is it already? Yeah. So let's say we revise our class 11th, 12th, etc. and return to the dimensional analysis. It is also known as the Buckingham Pine theorem. Have you covered this in UG before?
Yes, sir.
Alright. This should be fast. Do you know the limitations of Buckingham Pine? When I was also taught, I was not told why not to use it. When I first read it as a student, I realized, oh, this is great. I don't need to know anything. I just need to balance the dimensions and everything will turn out. But it turns out that there are a lot of problems. And it is the tool only for experts. Okay? So let's see. Alright. So our problem is at hand. Our question is, estimate the drag force, meaning find the scaling for drag force, what it is proportional to, without doing anything. by just observing the system and noting its dimensions, the dimensions of its quantities. Okay? And the Buckingham Pi theorem tells us that count number of quantities. How many quantities are there? N is equal to, in this case, 5. Count number of dimensions, the MLT, theta, वगैरह dimensions. How many are there? 3, right? Then n minus m, n minus m is equal to whatever number it is, and we call them pi I. So it could be pi 1, pi 2, pi 3. This would give us, this pi will give us number of dimensionless quantities. Are you with me? We went a bit, I made an error. We went a bit dimensions and then back again here. But I hope all of us are together. N minus m is 5. In this case, how many non-dimensional quantities are there? 2. It further says that out of this pi, one of them will be a non-dimensional version of dependent quantity. Is my writing understandable? So out of these pi, it could be one or more, but one of them would be a non-dimensional version of the dependent quantity. What do I mean by that? These are the quantity we listed. Which one of them is a dependent quantity and what do you think are the independent quantities? Out of these 5. What is dependent quantity? That's simple to ask first. Drag force? Drag force is a dependent quantity. Given you have U, the fluid density, viscosity and A. Another way of thinking about this is my personal way of thinking about it, is count the number of observables. Which of the things out of these are easily observable or easily capturable, if that's a word? These properties you easily know. FD is something that you might have to calculate. So this is your dependent quantity and these are independent quantities. And in this pi, what it's saying that now there are pi is equal to 2, right? So one will be non-dimensional version of this. So we'll get a non-dimensional FD or non-dimensional drag force. What do I mean by non-dimensions? It will not have any M, L or D. Okay? I'll get into the motivations. Why do we need non-dimensional numbers? Okay, I'll get to that in a moment. But let's just say that they are very important for experimentals. And the remaining pi minus 1 would be dimensionless numbers of the independent quantities, the remaining independent ones, U, density, viscosity and size. Okay? This is essentially Buckingham Pi theorem, and let's look at this part first. Let's find out what is FD non-dimensional. Let's call it FD star. How do we non-dimensionalize things?
Multiplying with a constant.
So let's say I have this table and the temperature here is 100 and here is 0. How would you non-dimensionalize the temperature here? T by the difference. So the outcome is that everything lies between 0 to 1. That is one of the examples of non-dimensionalization. So basically the idea is you divide the dimensional quantity by something that has the dimensions of that quantity. So FD has to be divided by something in order to make it non-dimensional. That has a combination of U, this, and this. Some combination should give rise to the units of force. So FD star into F into something. So meaning that you can write F. Yeah. So FD star is non-dimensional. F by this, some quantity we want to find. In textbooks, usually it's written as multiplication. It doesn't really matter. So what do I mean by that? Is that you can just add U to the power A, rho to the power B, mu to the power C, A to the power D. I mean, we could have also written in division. It would just be minus A. All these are unknown, so it doesn't matter. So the idea is we want to do simple logic and find what A, B, C and D are. Let's try to do that. So what will we do? What are the dimensions here? We will match the dimensions. Dimensions here is 0. Okay, but dimensions meaning M, L and T. There are only M is equal to 3. So we'll start with M. How many dimensions of M on the left? 0, right? Is equal to how many dimensions of M in F? This is multiplication one. F, did we write? I mean, look at the table. M L T minus 2, right? So it's just 1. You just have to match the exponents. Although it's multiplication, the exponents would just add up, right? 1. What about U? 0. So 0. Now what about this guy? B. Density. M. B. What about viscosity? Plus C. What about size? 0. Should I repeat this? Should I tell exactly how I got it? Please, I mean, this is first class, you can ask it. So what I did is, I mean, the preceding step I'm telling you now. I mean, FD star is equal to M0, L0, T0 is equal to force is what? MLT minus 2. Density is, velocity is LT minus 1 to the power A. Density is kg per meter cube ml minus 3 to the power B. Viscosity is ml minus 1 t minus 1 ml minus 1 t minus 1 to the power C, and then you have L to the power D. Okay? Now what I'm doing is I'm matching the exponent of each of these dimensions. I'm saying my relationship should respect each dimensions in its own, independently. So I'm saying 0 is equal to 1 plus 0 plus B plus C is equal to 0. And I'll do for L also and I'll do for T also. Shall I run this?
Yes, sir.
Alright. So let's do it for M, L. 0 is equal to others, fast ones. I just rubbed it for the right there. 1 plus A minus 3B minus C plus D. In my notes I have jumbled them a bit, so I am completely reliant on you now. And T is 0 is equal to minus 2, then minus A, plus 0, then viscosity minus C, and then size is 0, right? Now, how many unknowns and how many equations? Three equations for sure. How many unknown now? Three. Four, na? B, C, A, and D. How many solutions will it have? Under specified system, na? Infinite many solutions. Where did we go wrong? Where did we go wrong? I mean, we are following the logic, na? Every quantity should be made of some combination of these quantities, right?
But that A in the volume term in buoyancy force, तो सर A को भी ignore कर सकते हैं?
A को ignore करना है?
तो buoyancy force में rho particle और gravity को
हाँ,
तो volume है तो volume में A का term होगा ना?
volume maker, that's right. But drag, okay, now this is now, since I know the system, you can neglect A, but you will make an error. Because, I mean, this is all intuitive. I have not taught you any fluid mechanics yet. But imagine if you have a sphere, same buoyancy force, आप density को amp कर दो, make it small. Okay, like a dense compact particle. Same particle you make it large. Both will same. Yes. Do you think the drag force will change? It will change, right? If you, so simply speaking, if you have gone in aeroplanes or you have seen ships, they are designed in a way to reduce drag. Yes, if you are going very fast on bike, if you do this, you feel the drag, right? If you do this, you don't feel the drag, right? I didn't say how fast this ball was going, so it could be any Reynolds. Sorry for saying that. Any Reynolds regime, right? But we don't know what Reynolds is, right? But what I'm trying to say is that drag seems to be dependent on size. So it's not just this rationale of volume. There is another rationale. That's why I'm keeping it. That's a good observation. But you see, in order to defend my parameters, I'm bringing a lot of feel, a lot of intuition, and this is one of the criticisms and drawbacks of this analysis. That it's all vibes. Okay, all intuition. Sometimes intuition can be correct, sometimes it could be wrong. But we'll see how it could also, this analysis could help us in World War II or helped in World War II. Alright. Okay, forget about that. Okay, so what is the issue here? So A will be there. These quantities, trust me, they are fine. Some mistake is here. See, we have how many dimensions? M, L, and T, right? And we are taking how many unknowns? 4. The problem is there. We need to take any 3 of them. So you can remove any one of them. Okay? So let's take the easier one. Let's remove density. Then we will remove viscosity also. Don't worry. Let's remove density. So your FD star is F multiplied by U to the power I'm just going by my notes so that I don't make mistake. A to the power J, mu to the power K. Doesn't really matter. Just so that I don't waste time making mistakes. Now, I'll do the same exercise, match the dimension MLT. MLT minus 2, LT minus 1, L, and this is ML minus 1, T minus 1. This is easy. M is equal to 0 equals 1 plus 0 plus 0 plus K. Length 0 is equal to 1 plus I plus J minus K, and time 0 equals minus 2 minus I plus 0 minus k. 3 questions, 3 unknown. What is this? I, j, k kya hai? If you look here, k is minus 1 from the first equation. I is, from this equation, I becomes 1, na? Right? 1, right? And j is? Then you do some j. J will come out to be minus 1. Just check. Yes or no? What is now? Simply now, what is my non-dimensional force? F multiplied by, sorry, U. I would be minus 1. Yes, my all minus 1. So all will be below mu UA. Is this correct? How are you saying it's correct?
I should be 1.
Dimensionally it's correct.
I should be 1, I think.
I should be 1. No, I is minus 1. Minus 1. No, this calculation is correct, but I'm asking you, does this make sense? I haven't taught you fluid mechanics. Of course, this is Stokes' drag, we'll find it later. But at this point, please pay attention here. This is another criticism of this. Not only that this is all intuition, we have no way of knowing whether this is correct or not. Let's choose other combination. There will be other combination. Okay, so let's remove viscosity. What will we get? Instead of removing density, we reduce viscosity, retain density. And you can write F star is equal to F AJ UK rho L. Some exponents. Do you want me to do the exercise? It's just addition, subtraction. Right? If you do it as homework, you will find F star. You will find j equals to minus 2, k equals to minus 2, and L equals to minus 1. And you find that the non-dimensional force is F by rho u square a square. Density times velocity squared into radius squared. Does this make sense? Which one is correct? Are both correct? Are both wrong? You can remove now other terms. For example, you can try all these different combinations, and you can get numerous terms. But at this point, I will like to write two my main criticisms of this Buckingham pi theorem or dimensional analysis is that choice of n is arbitrary. Second, no way of knowing if pi 1, what is pi 1? The one non-dimensional number which will be the non-dimensional version of the dependent quantity. No way of knowing that is physically consistent. So this entire analysis is completely hinged on the first sentence that you write, or first observations that you make. Right? Okay, I'll write more criticisms later, but let's find out the other non-dimensional number. Meaning the pi 2. We found pi 1, right? And pi 1 has two versions. What is pi 2? Did you write the definition of pi 2? Pi 2 was completely independent quantities it will be made up of. Right? So pi 2 will be, what are the independent quantities? U, A, mu, density. Let's assign numbers A, B, C, D. Okay. Now, here comes criticism number 3 of dimensional analysis. Is that it tells us that pi 1, whatever pi 1 we get, will be some function of pi 2, pi 3 and so on. If we had more, it will be more. So my non-dimensional entity, FD, will be some function of this pi 2. That's what comes out from the Buckingham pi theorem. But it does not tell you if it's under root pi 2, if it's pi 2 square. It just tells you by the dimensional consistency that my non-dimensional drag force will be dependent on this pi 2, whatever we are going to find. Okay? So it's going to be some combination. So it could also be f under root pi 2 or pi 2 to the power 1 by 3 and so on. Meaning, one of these exponents are arbitrary. Does it make sense? Does it make sense? Let's say, assume A to be 1. Then you assume later A to be 2, 5 by 2, whatever you want to do. Assume A to be 1 and you are not losing any generality here. It's still general. Because of this criticism that I made, that Buckingham pi theorem just tells you that pi 1 will be related to subsequent pi's as just a function. That function is something that Buckingham pi theorem will not comment on. So if you take pi A is equal to 1, then can you find out, since you have MLT, can this relationship tell you what is BCD? Right? That's fine. You can start doing it. Pi 2 is equal to velocity Lt minus 1 what else is there? A L to the power B mu M L minus 1 T minus 1 to the power C, and density is ML minus 3 to the power D. What are the dimensions of pi 2? 0, 0, 0, right? It's not dimensional. What do you get? You can do M balance, you can do L balance, you can do T balance. What you will get is, on this slide, simply you will get, after doing all the calculations, K is equal to minus 1. Oh, sorry. Let me do it. C is minus 1, C is equal to minus D, so D is plus 1, okay, and B is C plus 3D, minus 1, C was minus 1, 3D was, B is 1. What is pi 2? What is pi 2? B. So it's u to the power 1. Fine, we assume that a is b, right? Sorry, a to the power is b, and this is 1. A to the power 1. Viscosity C. Density to the power d. This is your non-dimensional number. Does this make sense? I don't know. Of course, this is Reynolds number. So now in hindsight, we know that it makes sense since we have some expertise. So you know how that non-dimensional analysis works, right? It needs you need to know some transport phenomena, some fluid mechanics, some heat mass transfer in order to see if you're on the right track or not. The non-dimensional numbers you're getting, do they actually convey something or not? Yes? What is it saying now? The Buckingham pi theorem is that your pi 1 will be some function of pi 2. Since there are pi were only 2, there are two non-dimensional numbers. One was the non-dimensional version of the dimensional quantity, drag force. Second was this Reynolds number of pi 2. Now, I said that you could take A is equal to 2. If you would take A equals to 2, you would get these, you can do this at home, you would get 2, 2, 2, 2. So, it would be square of this. If you took A something else, it would adjust accordingly. Meaning, from dimensional analysis, it just tells you that this is a function of pi 2. It is not saying it's linearly proportional to pi 2. It has no power to do that. That is criticism number 3. I'll share you the notes for this one. Okay. Alright? Now, let's bring our expertise back. Let's say we know some fluid mechanics. And let's try to answer our questions. This drag force and this drag force. There are two ways of non-dimensionalizing drag force. This is the viscous way. This is the viscous force. That is the inertial force. That is, both are valid in different regimes, meaning in different situations. In my problem that I gave you, ball was dropping. If it's dropping at very fast speed, we'll see later that this is valid. If it's dropping at very low speeds in a viscous fluid, then this is valid. Okay? So F star, both are valid. But again, we never knew when we were doing the analysis, we didn't know that. And then this drag force will be dependent on Reynolds number. Non-dimensional drag force, friction factor. Have you heard that it is dependent on Reynolds number? Skin friction, right? Now, again, if you don't remember, that's fine. But it's just to highlight that this is a problem. So, both problems I have listed, many problems are there. What are the advantages? So, let's say we have an expert by our side and helps us through this process. What did we gain? Let's see what did we gain. Any questions? Let's say you're doing this experiment of ball dropping and you have what? Drag force is something you want to find, and you say that okay, it can be proportional to size, it can be proportional to velocity, it could be proportional to density, it could be proportional to mu. These four intuitive terms that you wrote, right? Now, if you are an undergraduate who hasn't done any non-dimensional numbers, how would you find the relationship between F and this and this and this and this? How would you, no, we don't know dimensional analysis. You have an experimental setup, okay? So let me make it simple. You have a simple pendulum, okay? You can do as many experiments as you want. So what would you do? You would change your angle, you would change your L. G you can't change, okay? And you will find how your omega is dependent on L. For small amplitudes you will do so that you can neglect this angle factor. So what, in order to get omega versus L, you do what, 10 experiments? To find that it's actually root L by Z or something you get, no? For simple pendulum. But basically I'm trying to tell you that if it was a simple system of experiment, then in order to get one curve, in order to get one relationship between the dependent quantity and one of the independent quantity, you would have to do at least 10 experiments to get a good graph. You could do 2 also, but then your graph will look bad. Right? So let's say we do 10 experiments for this, then 10 for this, then 10 for this, and then 10 for this. It's not just 10 plus 10 plus 10 plus 10. Because for every combination of, let's say you chose A, U, this, you have to do 10 viscosities. Right? But then for every combination you have to do it 10 times. So it becomes 10 times 10 times 10 times 10. How many experiments? 10 to the power 4. Just to know how F relates to these dimensional quantities. Now comes dimensional analysis. And it came, it was told by an expert and sort of made some sense. The logic is this, mota logic is this. This universe is made of fundamental dimensional quantities. There are 6 we all have agreed on: mass, length, time, temperature, intensity and current. The 3 of them don't matter here. Mass, length, time matter. So whatever you are seeing in this system, whatever these quantities are, have to do with some combination of these dimensional factors. We will do this dimensional consistent analysis, also known as Buckingham Pi analysis, and it will tell us that the quantity that you want to measure, the dimensional quantity you want to measure, can be made non-dimensional and could be represented in terms of some independent non-dimensional numbers, depending on the permutation combinations, what we saw. Right? Now, you did all that, you found that non-dimensional drag force was a function of Reynolds. Although all those criticisms are fine, you don't know what is the exponent n. But now you know that you only need to do 10 experiments. Why? You only need to alter the Reynolds number. So just prepare 10 Reynolds numbers and do the experiment, and you will get a curve, whatever curve you get. Friction decreases, right, as the speed increases. You have your analysis. So all those experiments would be meaningless. So this analysis of Buckingham Pi theorem was first popularized by Rayleigh, and around his time he was looking at lots of redundant experiments. And then what he found in his paper called as principle of similitude. So this was before known as principle of similitude, meaning dimensional similarity. So in that he found that there are lots of experiments that people have done which need not be done, and there are lots of bogus laws which are not dimensionally consistent. Right? Okay, so this is one of the examples. Now, after singing the praises of dimensional analysis, let me come back to criticisms by giving you another example and tell you that criticism number, how many were there? 3, na? Number 4 is, if you have one more non-dimensional number, things become tough. And the rules keep changing. Okay? Until now, we were all clear. Simple plus minus ho raha tha. Abhi iske baad let's see. Now, the next example is mass transfer from a falling particle. Let's do it. You remember I gave in the previous class, I gave an example. You have a catalyst particles dropping into the ambient liquid. Right? Multi-phase system. But you can make it easier by just having one particle dropping and it's diffusing out something. But since it's dropping at some velocity, there will be some convection. Now we don't know anything about this convection thing that I'm talking about. So how can we find a law, a rough law based on Buckingham Pi theorem? You have a particle falling, diameter 2a, radius is a. The question that, so this Q is also for question and this is also for the hint for dimensional quantity. Estimate flux from particle. And for this exercise, please keep that PDF ready that I have uploaded for you. I mean, you must have downloaded it, no? Just keep it with you. So that we don't keep deriving the dimensions, we can directly use them. Now, this is a system at hand. How many n's? How many quantities? One to already given flux, J, mass flux. What is flux? Amount of quantity per unit time per unit area. Yes. So we know this M per unit area per unit time. What else? Size. A. What else? So u velocity. This is dimension L. L p minus 1. और बताओ. Fluid density and L minus 3 4. Viscosity what else? What is flux dependent on? Constant difference, right? More the concentration difference, more the flux. So it should be one of the terms. So delta C is also there. Concentration units are mole per meter cube. So mass per unit volume. ml minus 3, right? So like density. Anything else?
Sir, mole तो एक अपने आप में fundamental quantity है.
I'm sorry?
Sir, moles तो अपने आप में fundamental quantity.
Oh, but you can convert it into gram per, you can convert it into by molar mass. If a particle is falling and emitting carbon dioxide or whatever, that has mass. Right? Anything else? So it's diffusing out, right? Diffuse out. So the diffusion coefficient also needs to be there. Yes? How many n's now? 1, 2, 3, 4, 5, 6, 7. Oh, 8 now. 8. Something is very good. Oh, 7. That is U separately. U already be counted. What is M here? MLT. No temperature difference, no light, no current. How many non-dimensional groups will you form now? 4. Now it's going to get difficult, right? Out of these 4, as I said, one will be the non-dimensional version of what we want, the dependent dimensional quantity. So it will be J star. The other 3 will be independent dimensional groups. Yes? As usual, we'll first start from J star and come across a problem. So J star, Buckingham-Pi theorem says, could be non-dimensionalized. So J star could be written as the dimensional J multiplied by all the independent variables to some unknown powers, and we match them. So U to the power A, rho to the power B, A to the power C, D to the power E, delta C to the power E, and mu to the power F. Again, we will come across a problem because we can only take 3 with us out of these 7. Which 3 to choose? Since you don't know anything about the system, you only have a feel about it. You'll only choose 3. So let's choose these 3. And then we can choose. I've just made some arbitrary choices in my notes. And I won't do the calculation again, but you can do it as your homework, since it's all plus minus. So if you take this, and if you take this question, J star is equal to J, U to the power A, rho to the power B, A to the power C. You do I need to do this? No, right? So B will come out to be -1, A will come out to be -1, C will come out to be 0, and you get J star is equal to J by rho U. Dimensionally consistent, but does it make sense? Makes sense with a question mark. Similarly, you could take other form, and you could do many other forms. I'm not saying there are only 2. Delta C to the power E, right? These 3. You will get, after you do your basic maths, J by D del C by A. Now, does this make sense? So, as usual, Buckingham Pi theorem, we have to call the expert. Yes, let's call Buckingham. What does the expert say? And then again, if I have shown in my notes, I'll upload, that if you choose other combinations, you'll run into problems and you'll run into some absurd, more choices to select from. But let's just take a look at these 2 and let's bring the expert here. What will this mean to an expert? That your flux from the ball or from the catalyst pellet is some density times velocity. Density times velocity. Is it like momentum per unit volume? Right? So it's as if if we had a catalyst pellet which is ejecting solute out at velocity u, then we could have written rho u. Also, the solute that it is getting ejected has density rho? No, right? This rho density was for what solute? Solute density. Solvent density, right? So it does not make sense that the flux has fluid properties here. So it doesn't make sense. Does this make sense? It is entirely made up of the properties of solute. Diffusion coefficient of solute. Concentration difference of solute. Particle size. So this also, to some of you who are experts here, you would instantly see it and say, this is the fixed law of diffusion. Huh? So of course flux can be written like this with a minus sign. But here signs don't matter, powers don't matter, it's just the relationship. So now this makes sense. But you had to call the expert. And what the expert is saying by these discussions with you is that you cannot treat, this is an important point, that you cannot treat the mass of the fluid as the same as mass of the. I understand that you may be tired, but just hold on for a few more minutes with me. You cannot confuse the mass of the fluid with the mass of the solute, otherwise you will run into these absurd things. So you need to make a distinction. You need to amend this Buckingham Pi and make a distinction. So in delta C mein jo m hai, whatever m is there, I need to make it solute m. And this delta m, this mass is fluid mass. So when I am doing my logic of matching dimensions, I am now cognizant that this mass is different from that mass. So you see what's happening? We are evolving our method. on the basis of advice from expert. So as I said in the beginning, this method is something that will work if you have strong intuition in transport phenomena. Alright? Okay, now once you make the distinction of this m separate and this m separate, then your m becomes 4, this becomes 3, and this becomes 2. 3 minus 1, 2. And then you do the whole exercise again and again. You got this part done. This is done. Now you need to find these two independent parameters. How will you find these two independent parameters? Same way we did before. Write down pi, let's say pi 2, and pi 3 we'll do later. Is some velocity times all the things you write down except j. Right? Because this independent dimensionless number will be made of the independent quantity. U to the power a, rho to the power b, a to the power c, d to the power d, delta c to the power e, viscosity to the power f. Again, can you go forward and match dimensions? Can you go forward and match dimensions? If you try to do that, how many equations you'll get? I mean, A you can take as 1. Same logic happening. We did this now. Because we don't know the power. 1, 2, 3, 4, 5. We need to let go of 2. So we need to make now various combinations. Yes or no? So you try various combinations and I'll tell you what will work. Is this guy matched with this guy and these guys matched with this guy. Rationale being, I'm going to keep my mass of the fluid separate, I'm going to keep my mass of the separate from the mass of the solute. On that basis, I can make different combinations. So I will never have a quantity in which I'm having density and delta C. Okay? So you can separate the two out, meaning you can write pi 2 is equal to U AC dd del CE, pi 3 is equal to U to the power 1 rho b AC mu f. You can solve this separately, Simple maths given in the notes, you can do it later. What you will get by solving 3 equations, 3 unknowns? Pi 1 will come out again to be rho UA by mu. Pi 2 will come out to be UA. I think I made a mistake. Oh, sorry. I've exchanged it, right? UA by D, delta C to the power 0 comes. When you solve, you will see that's 0. So it doesn't matter. And this is your Reynolds number, with what you saw before. This is some new number which you will later call as a Peclet number. What are we saying here? That these two non-dimensional quantity will determine my flux star. So my J star will be some function of Reynolds number, Peclet number. You might have seen some correlations already, but we didn't need to do any mass transfer to get this. But we had to call the expert. So some positives, some negatives. Yes? I'll upload the notes for this. I'll give you some simple exercises as homework for a simple pendulum. And in exam, don't worry, I will not ask the mass transfer sort of examples. Any examples which have pi greater than 2. So it will be just one of them, not two. Because again, you have to call the expert. An exam you cannot call the expert. Phone a friend option name. Right? So again, but as I understand, this is not like a foolproof method, and I wanted to highlight it because many of you have studied Buckingham Pi theorem, but very seldom we talk about its criticisms, and this is the reason why we need to become experts, so that we can be like Geoffrey Taylor, who I talk about. Just give me 5 minutes. There's a interesting Taylor, and he did a very nifty calculation for World War II. Basically this, so the first atomic bomb, some of you have seen Oppenheimer?
Yes.
Right? So this happened, alright, and then a lot of scientists were called on the site, and a lot of pictures were taken of this blast. Okay, a lot of time snapshots were taken. This was not done next to a Empire State Building, but this is just for reference of big explosions. And if you superimpose all of these, you will find that the blast grows in time. And the question then was, people not, like there were no fundamental equations then for a nuclear blast. We just had discovered this explosive device or invented it. And the question around that time was that, can we say something about this blast? Can we estimate the energy of this blast or the rate of growth of this blast just by pictures? Same way we asked the dimensional analysis question, right? I said, let's assume that you don't know anything about the system, you don't know transport phenomena, and you get some numbers, and then you call the expert and ask. At that time there was no expert. Even Geoffrey Taylor was not an expert. Alright, so there were these snapshots, and what you can do is you can take the radius and plot it with time. Okay, it will come later. Okay, so the question is, can we decipher the strength of the bomb just from its images? G.I. Taylor said, let me assume something, that the kinematics of the explosion is completely related to the mechanics of the explosion. Meaning, the growth of this bubble-like thing, or the explosion bubble, is completely dependent by the mechanics of the explosion. So the radius will be completely dependent on some E, energy of the explosion, and it will grow in time and whatnot. What else it would contain? So now again, same question that we are asking ourselves at the start of every question here in Buckingham Pi theorem. What is N? This is Taylor, and he asked what is N, and he had many options. So energy, of course, energy of the blast, radius, time, this grows in time, density of the air, viscosity of the air, and temperature difference. I mean, you could see these as also being viable candidates, right? But these were discarded because from the observation that temperature actually grows after some time. When the blast has happened and some time has elapsed, some few seconds have passed. But this blast happens over very short time span. So in that time span, there is no temperature rise. So that has to be neglected. In that time span, viscosity also has to be neglected because these are very, I cannot explain to you right now, but these are very fast flows. There's something called inviscid flows. So air has very low viscosity. Okay, so the viscous effects were assumed to be negligible, and it worked out. Okay, so some luck is always involved in these things because you don't know anything and you're trying to find an analysis. Alright, so N is this. If you calculate M, it will come out to be 3. M and T. Dimensional groups 1, meaning it's only 1. So energy, that's your desired quantity, it will be non-dimensionalized and it will not depend on any other parameter. So the non-dimensional entity will be just 1. So that what you can easily find. So this is your homework. I'll list it all out for you. That E star will be E by this. This is easily, you can easily find it. That's what Taylor did. And what you can observe from this very simple analysis is that energy decays much sharply in space than in time. So as you go even some distance away from the center of the blast, the energy will decay rapidly, but it will decay less rapidly with time. Okay. But is this even correct? Right? So Taylor must have asked, this I got. But is this correct or not? So he looked at the images. This was this blast, and this is your radius of the blast and time, but these are on log scale. You know the advantage of log scale? Don't know the advantage of log scale? So let's say radius is some proportional to some power alpha. If you plot it on log scale and do experiment, log r proportional to alpha times log t, right? So the slope gives you the scaling, the exponent, right? So you can find the slope, and this came out to be 5 by 2, 0.4. This came out to be 0.41 roughly. And this was given to Taylor. Bhai, dekho, take this and tell us. So now, given this, there's only one non-dimensional number. It cannot depend on any other non-dimensional quantity. So it has to be a constant. So if this is constant, you can take r here, and what you can write, the radius of the blast is proportional to t to the power 2 by 5. Yes or no? Because see, as I said, pi was 1 and only E star could be non-dimensionalized. Are you with me? Okay, but there are some problems here. It doesn't match here. It doesn't match here. I write it here for other reasons. Okay, so that exponent 2 by 5 is what? 0.4. So it matched, and the paper was not published for 5 years because it was a government secret. It was published 5 years later. So this is also known as the Taylor-Sedov exponent, Taylor-Sedov regime, and you must have seen this Beirut explosion, right? This was basically some explosive fireworks, mishandling of them, and then it exploded with a lot of, E energy, unfortunately. And then there was some analysis recently where they calculated this radius of this explosion from various footages they got, and they found that after some time it enters the Taylor regime, Taylor-Sedov exponent 0.4. Even not just this, even supernova explosions. Once the initial blast has gone, it enters a Taylor regime. What I'm trying to say with this is that if you are an expert in transport phenomena, you can solve problems of outside your curriculum, and they could have far-reaching consequences, right? So with that, in the next class we will begin the fundamentals of transport phenomena. You have to be comfortable with equations. So the calculus of transport phenomena will begin. Alright? I'll share the assignment questions with you.